This is part one of a series of videos about simplifying rational expressions. And this video is just going to look at single terms, single rational expressions, not operations. So we're going to go over a couple definitions, look at what a giant one is and how it's used, simplifying by finding giant ones, looking at excluded values, and then go through some examples. So a rational expression is an expression that can be written as a ratio of two polynomials, ratio being a fraction, and we also need to know what polynomial means for this definition. So a polynomial is an expression that can be written as the sum of terms in the following form. You can have a coefficient of any number times your variable to the power of a non-negative integer, meaning a whole number that is not negative, but it can be 0. Some examples of polynomials would be 1/4 x to the 7th minus 5x squared, or negative 3/10 times x to the 5th plus 2. A whole number fits this form, for example the number 2, because it can be written as 2 times x to the power of 0. And so just whole numbers or fractions, decimals, whatever, but without an x term are still polynomials because they can be written as times x to the power of 0. Something that is not an example would be x to the power of 1/2 because it has a fraction in the exponent, or x to the power of -3 because it's got a negative number in the exponent. So going back to our definition of a rational expression, we could do something like negative 3/10 of x to the 5th plus 2 over 1/4 x to the 7th minus 5x squared. So a ratio or a fraction of two polynomials. So the numerator and the denominator are polynomials. Remember that we can just have a whole number, so I could have something like 2 over x plus 3 as a polynomial, as a rational expression also. A giant one is a ratio or fraction of two equivalent expressions. So some examples here would be 5 over 5, or 2x over 2x, or 5x plus 4 over 5x plus 4. Anything where the numerator and the denominator are the same. Let's look at what some of these look like graphing, and then we'll come back to this page. So if I graphed y equals 5/5, I'm getting a line that is horizontal that goes through y equals 1. So for any x value, the output is going to be 1, which makes sense because 5/5 simplifies to be the number 1. If I look at y equals 2x over 2x, I'm seeing the same picture. So if I plugged in x equals 3, I would get y equals 6 over 6, which simplifies to 1. So when x equals 3, y equals 1. This makes sense. The only x value that will not give you an output of 1 is x equals 0. Because when I plug in x equals 0, I get y as 0 over 0, and this is undefined. I can't divide by 0. And when I use Desmos to look at what happens when I click on x equals 0, I see that it says when x is 0, y is undefined. So even though 2x over 2x simplifies to be the expression 1, the graphs are not equivalent when x equals 0. So the graph of 2x over 2x and the graph of y equals 1 are exactly the same except for at x equals 0. So when we simplify that, we're going to say 2x over 2x is equivalent to 1 except for when x equals 0. And we'll talk about this. This is called an excluded value. We'll talk about that in a bit. Okay, and the last one, 5x plus 4 over 5x plus 4, we're seeing the same graph because this simplifies to be 1. But we want to know, well, which value of x will make the denominator 0. So I'm going to set the denominator equal to 0 and solve to see what that will be. 5x equals negative 4, x equals negative 4/5. So when x is negative 8/10. And I'll look at that on Desmos, and there it is. Every other input maps to an output of 1 except for negative 8/10. So looking back at our examples of giant ones for a minute, we want to think about why these are important. So each of these terms has a value of 1 for almost all of their x values, which we just saw on the graph. And 1 is a really important number because anything times 1 is itself. So if I take an expression like 2x plus 3 over 5, and I multiply it by 2x over 2x, this is going to be equivalent to just 2x plus 3 over 5, because I took something and I multiplied it by a giant 1. And we're going to have to be careful about the excluded values, those places where an x value gives you an undefined output, but we'll talk more about that in a little bit. So let's look at a few examples of how to use a giant one to simplify rational expressions. I'm starting with 4/10, and I want to first rewrite the numerator and the denominator as a series of products so I can see where some giant ones might come from. So 4 can be written as 2 times 2, and 10 can be written as 2 times 5. And so I see that there's a product or a factor of 2 on the numerator and the denominator, the top and the bottom. So I can rewrite this expression as 2 over 2 times 2 over 5. 2 halves times 2/5. And then I'm seeing that there's a giant 1 here, and 1 times 2/5 is just 2/5. So 4/10 is equivalent to 2/5, which we totally agree with because we know how to simplify fractions. Looking over at this next example, I've got 6x squared times 3x. So I'm going to write this out as a series of factors. I've got 2 times 3 times x on the numerator, and 3 times x in the denominator. So I see that there's a 3 and an x in both the numerator and denominator, and I have both parts written as a series of factors, so they're in factored form. So I can write a giant one here as 3x over 3x, and my numerator will be left with 2x, and my denominator will have to be 1, so that when I multiply my fractions together, I get a denominator of 3x. And I've got a giant 1 here. 1 times 2x is just 2x. And then I have to think about, when I graph this original expression, will there be any x values that give me an undefined output? Because when I graph y equals 2x, there won't be. And so what I'm thinking of is, for excluded values, which inputs will make the original output be undefined. And so I'm looking at which value of x will make 3x equal 0, and that's x equals 0. So going back to my original problem, 6x squared over 3x can be simplified to 2x using giant ones, but we want to say that they're not equivalent when x equals 0, because that's an x value that makes the original expression undefined, but not the simplified expression. Okay, so here is something that looks a little bit more like what we would be seeing in class. This rational expression already has a factored numerator and denominator, so I'm just going to start by looking for giant ones. I see that both numerator and denominator have a factor of x minus 2, so I'm going to choose to rewrite my expression as the product of x minus 2 over x minus 2 and x plus 4 over x plus 5. Here's my giant 1, and anything times 1 is itself, so this expression can be simplified to simply x plus 4 over x plus 5. We're going to think about those excluded values. The question is, which x values make the original expression undefined, and that would be when x minus 2 times x plus 5 equals 0, because I can't have division by 0, which means I can't have 0 in the denominator. And here I can use the zero product property to say x minus 2 equals 0 and x plus 5 equals 0. So this gives me excluded values of positive 2 and negative 5. Going back to my problem, x plus 4 times x minus 2 divided by x minus 2 times x plus 5 can be simplified to x plus 4 over x plus 5, but they are not equivalent when x has a value of 2 or negative 5. And so this is my final simplified expression. Let's look at the graph real quick. So here I set the original expression equal to y and graphed it. That's in red. And then I set the simplified expression equal to y and graphed it, and that's in purple. So when I set the purple graph to be a dotted line, we see that those two graphs are exactly the same, which means that the expressions are equivalent. For all values of x, they give the same output. But what about those excluded values? So we'd said x couldn't be positive 2 or negative 5. And so when I look at those two x values specifically, this is what happens. At positive 2, the original expression, the red one, has an output that is undefined. So looking at our other excluded value, x equals negative 5, what I've done is I've put in a dotted line through x equals negative 5 because there's actually a vertical asymptote here. So our red graph, the graph of the expression, the original expression, is approaching the blue dotted line but never touching it. So as the inputs get closer and closer and closer to negative 5, the outputs either go up to positive infinity or down to negative infinity, which is an idea that we'll think about in pre-calc and then really use in calculus. But what's important to know here is that there is no output when x equals negative 5. And we can justify that to ourselves by thinking about how if we plugged in x equals negative 5, we would get 0 in the denominator because one of our factors would have a value of 0. So looking at the simplified expression, we see that in our first excluded value, x equals 2, there is an output of 857 thousandths. So when our original expression was undefined when x equals 2, and our simplified expression is not. So that's why we have to say that the expressions are equivalent, but not at positive 2. Now our simplified expression also has a vertical asymptote at x equals negative 5. So even though that's the same for both simplified and original expression, we don't have a value, an output that we can compare when x is negative 5. So our concept of equivalence is that for every value of x, or for every value of the input or inputs, the two expressions will have the same output. So when I plug in x equals anything, I'll get the same value for both expressions. But when I plug in x equals negative 5, I get an undefined value, which is just not something we can compare because it's not defined. So our final answer here is that x plus 4 times x minus 2 over x minus 2 times x plus 5 is equivalent to x plus 4 over x plus 5, but x cannot have a value of positive 2 or negative 5. Let's look at a couple more examples. So here I've got a rational expression, but the numerator and denominator are both in standard form. So if I want to be able to rewrite this as a giant 1 times something else, then I'm going to need to factor the numerator and the denominator. So I'm going to go through this quickly, but if you want practice factoring quadratic expressions, be sure to check out that video. So here I want these to add to 4x and multiply to negative 21x squared. So that could be 1 times 21 or 3 times 7. And so I'm going to use 7x and negative 3x. Here I've got x times x, negative 3 and 7. Okay, so my numerator can be rewritten as x minus 3 times x plus 7. And I'm going to erase that to make some room so that I can factor my denominator. I'm going to add to 15x and multiply to 14x squared. So that's going to be 14x and x. So my denominator can be written as x plus 7 times 2x plus 1. So I'm seeing here that my giant 1 is going to be x plus 7 over x plus 7. And the other part of my product will need to be x minus 3 over 2x plus 1, so that when I multiply those two fractions together, I get back to my original expression. So anything times 1 is itself, and so multiplying by that giant 1 doesn't change the value of x minus 3 over 2x plus 1. And I have to say that the simplified expression is equivalent to the original, but not when I plug in the x values that make the original denominator equal 0. So that's going to be when x plus 7 equals 0 and when 2x plus 1 equals 0. So this is negative 7 and 2x equals negative 1, x equals negative 1/2. Okay, so the simplified version is x minus 3 over 2x plus 1, but x cannot have a value of negative 7 or negative 1/2. Here's another example, and here I will need to factor the numerator and denominator again. But before I do that, I can see that the terms in the numerator have some common factors, and in fact the terms in the denominator also do. So I can see in the numerator, it looks like 15 multiplies into 30, 75, and 180. So I'm going to factor out a 15, which leaves me with 2x squared minus, 15 goes into 64 times, so it goes into 75 5 times, minus 5x. And then if 15 goes into 60 4 times, and 60 goes into 180 3 times, then 15 times 12 would give me 180. So I've just factored out a 15 from the numerator, and then I can see that a 5 multiplies into 10x and into 15. So I've now got this expression. And I need to continue factoring, so I'll need to use an area model to factor 2x squared minus 5x minus 12. So I'm looking for something that adds to negative 5x and multiplies to negative 24x squared. 1 times 24, 2 times 12, 3 times 8, there we go. So negative 8x and positive 3x. And I can now rewrite my expression as 15 times 2x plus 3 times x minus 4 over 5 times 2x plus 3. In fact, I can also rewrite the 15 as a product of 5 times 3. So I'm seeing some giant ones here. I'm seeing 5 times 2x plus 3 over 5 times 2x plus 3 multiplied by what's left, which is 3 times x minus 4 in the numerator. And it would have to be a denominator of 1 so that when I multiply my fractions back together, I get a denominator of 5 times 2x plus 3. So when I take out that giant 1, because multiplying by 1 doesn't change the value of the expression, I am left with 3 times x minus 4 and I don't need to write divided by 1 because that doesn't change the value, and my excluded values are going to be the values of x that make the denominator equal 0. So I'm thinking about which value of x will make 5 times 2x plus 3 equals 0. So a value of x that makes 5 equals 0, or that makes 2x plus 3 equals 0. And it's clear that there's no value of x that will make 5 equals 0, so I'm just solving the other equation. 2x equals negative 3, x equals negative 3 halves. So I'm saying my expression is equivalent to 3 times x minus 4, but x cannot be equal to negative 3 halves. So let's look to make sure that the graph supports the simplification that we just did. So when I set the original expression equal to y, we get a graph that looks like this. And when I set the simplified expression equal to y and make it a dotted line, we can see that the expressions are equivalent as far as we can see on this graph. It looks like every input maps to the same output. Now we want to check out the excluded values. In the original expression, when I have an input of negative 1.5, I get an output that's undefined. Remember, we got negative 3 halves as the excluded value because it was the value of x that made the denominator equal 0, and we can't divide by 0, so we get an undefined output. But in the original expression, when x equals negative 1.5, y has an output of negative 16.5. So we say that these two expressions are equivalent for every value of x except for negative 1.5. So that's my last example for this video, but in the next video we're going to be doing multiplication and division with rational expressions, and then after that addition and subtraction with rational expressions. So you'll see lots of examples of simplifying single rational expressions in those videos.